This presentation is delivered by the Stanford Center for Professional Development.
So thank you very much for coming in today, even though it's the first week of the year and you may have been tempted to expand the vacation a little bit longer. It's very nice to be back here and tell you a little bit more about what we've been up to over the last few years. And so I was thinking long and hard about how to call this talk and how to explain what we're doing. And I still did not come up with as brilliant an idea as Andy did with the control bits being one-to-one with the gates versus instructions which are small, controlling an entire chip. But I think that will give me personally quite something to think about in the next few weeks. Instead, what I'm going to focus on is the vertical versus horizontal way of doing computation. In the horizontal way, you think of somebody making a microprocessor, somebody else making an operating system, somebody else thinking about the software layers on top, and each one of these has to work for all applications, right? And we are taking a vertical approach to this, where we say, let's look at what we can do across the entire stack of things. And so in order to do that, we need to look at things slightly rotated. So if you look at it from a different perspective, you sometimes see things that other people don't see and have opportunities to do optimizations and to match what you're doing to what you would like to have as a result in a slightly different way. And so to define a little bit better what it is that I mean with that, there is the idea of multiscale. You're looking at a problem on multiple scales of abstraction, multiple levels of abstraction, at multiple sizes, at multiple granularities, and really looking at what it is that you can do to optimize the entire system to save energy, to run as fast as possible, to save space, to make it mobile, or to move things from batch processing into real-time activities. And so that's really where you can look at the transistor level, the bit level, the arithmetic level, microarchitecture level, parallel node level, complete system level. And once you look at all of these things and you go top down, then you go bottom up again, and you play a few times back and forth, you figure out what it is that you can do on each of these levels. Like on the complete system level, you would like to balance compute, storage, and I/O. On the parallel node level, you would like to maximize the utilization of your computation and your interconnect or communication. And people would talk about the computation to communication ratio of their parallel programs. On the microarchitecture level, you probably want to minimize data movement, because moving the data around is the thing that takes a lot of time, takes a lot of power, and is just very inconvenient. There is the arithmetic level, where actually we want to compute something. So what is that thing that we want to compute? Well, there's going to be numbers going in, numbers going out, but it's not really numbers, right? It's discretized representations of these numbers using bits. And so you have to think of range, precision, accuracy, discretization in space and time and value all together. And so today scientists all worry about time and space, and they don't like to worry about value. And the way they do that is they just say, well, it's going to be double precision floating point, and whatever that means, that's just going to be good enough. And if that doesn't work, we'll call in one of the experts who knows how to fix that. And if it costs 100 times more to pay for the electricity to run that computation, that's not my problem. I really don't care about that, because somebody else is going to fix that. So here, by looking at this discretization as time, space, and value, you get to play around with these things in an interesting way. On the bit level, the way you encode your problem can have massive impact. As you know, if you think about an actual physical problem, you look at the physics, and then you say, well, I'm going to encode the physics in a certain way. I'm going to encode the Earth as being these parameters, and they're going to be able to take these sets of values. That's an encoding. And if you pick an optimal encoding for that, clearly that can improve the efficiency of the computation. And finally, as you go down to the transistor level, you're actually playing with voltages and assuming that these mean 0 and 1, but you can actually look at that as activities that take power, take electricity, and can look at that. So here is a conceptual view of what it is that we're talking about. There is CPUs in the system. There is Dataflow engines in the system, which we are prototyping on FPGAs. And there is an InfiniBand network that we use to connect these two worlds together flexibly, because you never know how many of the CPUs and how many of the Dataflow engines you may need at runtime. And so in a flexible environment, you may have an application that takes a few of these and a lot more of these down here. Another application may take lots of these up here and just a few of these down here. And so we have a multi-user, multi-application environment that manages all of this for us. And we have the different levels of abstraction as well, with the processors, the complete system that you have here, down to the chip, the arithmetic units in here, the memory, the bits, and the transistors that drive these. So that's kind of the global picture. And I thought of starting this talk with the result and then working backwards on how we're arriving to that. So once you put all of these things together and you take commercial applications and you put them out there and you optimize them and you run them and you compare against different types of technologies. Here, this is a comparison against the latest CPUs that you can buy in high-performance computing, so high-end servers. So you take the latest Dataflow computing solution that we have, and you compare it to the latest processors that you can buy on the high end. And you see a ratio of between 20 and 60 times in terms of the size of the machine. So you have a certain size of the machine. You say one of these nodes does the same amount of computation as 20 to 60 of these others. And the examples here, this is a PDE solver for acoustic modeling in geophysics, and that's solving the acoustic wave equation with a finite difference model. This is a local area model, which is coming from weather prediction. So there, the pressure is being modeled on two-dimensional finite difference planes that are then being stacked on top of each other. This is trace processing also from the seismic industry. There is imaging. There is fluid flow, which is basically two fluids mixing inside of a material and seeing how one fluid pushes the other. And then this is mainly the activity that we talked about in one of these previous talks here, the finance activity that we've done with JP Morgan. And Stephen here knows a lot more about that. So I'll just skip over to the next bit. So what does this really mean? So if you look at, let's say, a 33x multiple as we had on the previous slide, you have 4 days going to maybe 3 hours. You have scenarios that you're computing. You may be able to compute 10 risk scenarios going up to 330. If you look at the power consumption, 1 megawatt going down to 36 kilowatts. If you think about it in terms of spending, you say for every $1 million that you spend on a computer system with a standard microprocessor system, over 3 years, you may be generating 1 more million in terms of electricity costs and just operational costs around that. Air conditioning and just maintaining the environment. And with that, this basically drops down by more than 10x for every dollar that you spend on buying it. So there is there are different dimensions that you can look across and say, given that I have a budget, given that I have a power budget, a space budget, or just a weight budget in terms of carrying it around, there is different consequences. So then the question is, these numbers just look very much out of whack with anything that one sees. Typically people talk about 10 or 20%. Clearly there is the downside of this. And the downside of this is that there is effort involved. You actually have to spend effort to move things over into this world and optimize them one application at a time. You can't just take your open source applications and move them onto this technology. It takes effort, it takes some time, and that's what this talk is really about, to show you how we do this. So what we have here is the main components. We have the architecture, which is basically a static data flow architecture, and there's a lot of literature on these types of architectures out there. We will have the management of the transactions, moving the data around in that kind of environment, optimization of the data movement across the machine. There is the application programming interface. How do you actually do it? What's the programming interface? How do you get programs written in C++, Fortran, or any other language over into this world of computing in space? And then the application areas, where I'll talk a little bit more about particular applications, and then Stephen is going to follow up with a little bit more in-depth analysis of the risk domain, where we're looking at computing scenarios across wide ranges of parameter changes. So I'm going to go out on a limb here and simplify the problem a little bit. Of course, the actual computation is a lot more complicated. But a very, very simple pipeline, if you just think of it as a string of units with the stages here. If you want to compute these 5 operations on a large stream of data, right? And you say, I have a certain data rate that I want to reach. I would like to compute 1 gigabyte per second of results, right? How would I do that? Well, you need to stream the data in here at 1 gigabyte per second, and you stream it out here at 1 gigabyte per second, right? And so the clock frequency for this, the minimal clock frequency that you can use is the data rate, right? You need a clock tick. You need a tick of the clock to get the result out. Otherwise, it's not going to be easy to manage. You could get more, but then you're having signals floating on the wires, and that's all very, very inconvenient. And so 1 clock tick per result, if you look at the power consumption equation, you see, well, it depends on capacitance, voltage, and the frequency. So in order to minimize power, if we assume that the capacitance and the voltage is the same, then all we need to do is minimize the clock frequency. If we want the minimal power for a particular computation, the minimal power rises if you have the minimal clock frequency. What is the minimal clock frequency? It's the data rate, because you cannot have a lower clock frequency than the data rate. And so then all you have to convince yourself is that the largest chip that you can buy from most major companies today are driven by whatever can be manufactured and put into a package. So the largest chip from company A will probably be as large as the largest chip from company B. And that will set the capacitance, and then one can argue around about the voltage here a little bit, but I won't be doing that too much. My argument is really more about the clock frequency being minimal, and for a set of capacitance and voltage, that gives you the minimum power consumption here. And so here is what you get. You get an assembly line, and the computations come out, and they plop out one at a time. And interestingly, in the manufacturing world, this is also the most efficient way that people figured out how to manufacture things. If you want to manufacture a lot, if you just want to make 2 or 3 of something, then this is, of course, overhead, because you have to build a whole factory, and you have to make this assembly line and hire people. You could just have made one in the meantime. But if you want to make thousands of them, then it makes sense to sit down, build the factory, make the assembly lines, make the whole thing move here, build a nice track, get the thing to move, and plop them out one at a time. And so now there are a few, I'll call them theorems, but really, I guess, these are more just statements on what I see as conclusions from all of this, which is that the time to compute 1 million results is equal to the number of results per clock cycle times the clock frequency. Right? So you have the clock frequency as it plops through. This is the number of results you're going to get. So you can compute how long it will take to process, let's say, 1 million numbers. What this also means is that it doesn't depend on the number of operations that you have in here. So the computation time, the time it takes to compute, now only depends on the amount of data. It doesn't depend anymore on the number of operations, as long as the number of operations is a lot smaller than the amount of data. So if you look at computation, you have less arithmetic, more data, then you can just project how long it will take to compute this. Now the second piece is that for any desired data rate of results, the minimum clock frequency is equal to the data rate, right? Because you cannot have a lower clock frequency. And then finally, assuming the capacitance and voltage is not causing further trouble, the minimal clock frequency brings the minimal power consumption. Yes?
I get the feeling that you're leading us down the path that power is the thing we want to be worried about. But if just using what you've given me, you lower the frequency and maybe you save some power, but if your results per cycle is the same, it takes longer, you spend the same energy. And I would claim it's the energy you want to look at.
Okay. That may be true.
So changing the frequency does nothing.
Right. So you also need to be faster. So as long as you're not slower, if you are a lot faster and you use less energy, then you've saved the power. So I can talk to you about this after the talk, but I think that there is a way to combine that with the execution time. This is just the power argument. Right? Clearly, if you take longer to compute and you reduce the clock frequency, then you haven't gained anything.
Right, exactly.
You're missing the frequency. The energy doesn't go up by, it's not linear related to frequency. As frequency goes up, power consumption goes up by a power of 2 or 3.
So it's a power and time argument, of course, and you need to look at how much time you're spending. In terms of the overall structure, drilling down a little bit into the details, there is a certain amount of control flow that you have in an application, and you can put some of that over on the microprocessor. You can put some of it into the Dataflow architecture and have a certain amount of local control flow here. And you can have also a certain amount of control flow in switching out different configurations here into the chip. So really you have 3 types of control flow. And the rest is the data flow through this chip and the memory that you have here. Now I've drawn this very small, but this can actually be 24, 48, 382, 384 gigabytes, I believe. So you could have a substantial amount of memory here attached to this ring where you're rotating these things through. And so all you have to do in order to compute is to pass bits from one side to the other. And I'm grateful to Bob for this particular slide. It's one of my favorites. But instead of looking at that for too long, once you look at this, what can you do with that? Well, it really spans the idea of data, networking, and computing. So if you think of the Dataflow technology here in the middle as providing connectivity, storing data, and providing computation all in one go, you can build machines that deal with the computational part, the connectivity, or the data bit. And so there are some examples around here of what we've done or what could be done from PDEs and algorithms on the computation side to connectivity, where in finance we are doing low latency trading, working with exchanges, and just basically moving data packets around in the network, over to data where there's a lot of potential on the database side, dealing with expanding and compressing data, caching it, searching. All these types of activities are really interesting. And so you put that together, this is how they actually look like, and there are a few here also, both in the geophysics department and in the Gates building. There is a C-series which combines the CPUs and the Dataflow engines. There's a Dataflow appliance which sits on InfiniBand. And there's a networking appliance which kind of sits on a network and works on the data passing through with a TCP/IP stack, with decoding of the data, and just looking into the packet, layer 3, 4, 5, 6, 7, any one that you want. So getting back from the real world out there, I think some of you may have seen this question. It's one of the big questions out there. Does anybody know the answer to that one?
Presumably base 13.
Base 13? No. It's just regular decimal.
408.
408,
Yeah.
looked up on a calculator. Very, very good. So I gave this talk, or at least this slide, a while ago, and I gave handouts. And on the handout, I had a different number. I changed this to 16. It was very mean. And I asked the same question, and of course, the answer came very quickly as 408. Because somebody just looked it up on the handout. Oh, it's written in the handout. I'll just read it out from the handout, right? And so given that the number was wrong, obviously that didn't work out. The nice thing about this is that it tells us something about thinking. So I've stolen this question from this book by Daniel Kahneman, who got the Nobel Prize in Economics, which is a brilliant piece of work, talking about 17 times 24 and saying that you look at, let's say, back 2, and there is no way that you can prevent yourself from reading it. There is no way that you can say, no, I'm not going to, as long as you look at it, your brain will read it, and it will tell you what it is, if you want or not. It's irrelevant. This, on the other hand, takes effort. You would have to actually spend effort to calculate how much it is. And it's possible. You know how to do it, and you can do it, but you're not going to, because it's too much effort. And that's because it requires you to use system 2, and this is the naming that Kahneman has for these 2 bits of your brain. System 1 is very fast, hard to control, and it will tell you that this number is about 400. It's somewhere there, and you know it's about 400. You're not going to say because it doesn't make any sense to say that, but you know it's about 400. You don't know that it's 408, and you're most likely not going to put in the effort to do it because it's not useful. System 2 is slow, easy to control. It's also very lazy. It's going to try to prevent, to spend the effort to actually do this as much as it possibly can. And the reason is because it's an energy optimization, right? You want to be able to do as much computation as possible at as minimum energy as possible. And so, let's just kind of take that as a piece of information that's a nice way to think of things. And then I just dug back to one of my favorite statements. And I like particularly how this was written. It says that we are forced to recognize, really suggests he's not very happy about it, he doesn't like it, he doesn't want to have it, but something has forced him to recognize this, that there's this possibility of constructing a hierarchy of memories, which is going to create pain and suffering for the remainder of mankind. And each of these is going to have greater capacity than the preceding one, but it's going to be less quickly accessible. And so regardless of any progress that we've made, any memory technology that we've seen so far, if it's bigger, it's slower. If it's smaller, it's faster. It's just how it is, right? So the bigger you make the memory, and here it is. It's all already laid out very nicely. So we have our 2 problems laid out for us. We have...
If somebody invented a small, slow memory, nobody would care.
Yes?
So we're throwing away, if we do the standard, 4-coordinate graph, there's areas where even if you had something, nobody cares.
Well, it is true that I'm assuming that every player in the game is going to use his dominant strategy in order to accomplish his task.
Okay.
Right? So you want to do the best you can on all fronts. Of course you can ruin it, but if you do the best you can on the small memory and you do the best you can on the big memory, then it turns out that you have that. And so now combining these 2 things and just saying, well, let's compute a function. Let's compute an elementary function, very simple. 1 input, 1 output. It's not too complicated. And you say, well, we could look it up in a table. It's just a function, right? Or we could use arithmetic. We could do polynomials, and we could do rational approximations and all kind of other wild things. It turns out that the optimal way to compute it in terms of the time it takes to compute it, the resources it takes, is somewhere in the middle. It's a trade-off between remembering some of the things and computing some other things. And so that's a very nice trade-off that you can play as an optimization on the microarchitecture level. And just an example, we've done a paper a little while ago with a brute force method. So just enumerated all of the different ways, or many different ways, of precision and range. So you want a certain precision for your sine or cosine, and you have a certain range that you are looking at. Given the range and the precision, there's a different method that is optimal. And there's quite significant differences in the method. So you can see for sine, with 12 bits of range and 4 bits of precision, it turns out that the polynomial of order 2 is the ideal thing with a table that gives you the two coefficients at time. And the precision that you want for the 2 is 9 and then 31 bits. So there is different optimal ones. This is a polynomial. This is a table with a polynomial. And up here, as you get more precision and more range, you're going to start to see TP3, which is three coefficients and bigger tables. But there's a different optimum point for how much memory and how much compute you want to do. And so that's just an example. For large programs, you want to do such an optimization by thinking about the algorithm and figuring out how much you want to remember, how you want to encode your problem, what is your data structure, and what is your arithmetic, what are your computations. And that trade-off of how much you store in memory and how much you actually compute is one of the key trade-offs in optimizing the balance between how much you need to communicate afterwards and how much you need to compute. But in order to optimize a computer system that way, you need to understand the partial differential equation. You need to understand the finite difference method. You need to understand what the scientist has in mind when he wrote this and what he actually wants to compute. And so that's slightly inconvenient for somebody who lives in the horizontal world, who just wants to optimize a microprocessor without understanding how imaging works or how partial differential equations get created from a physical problem. So that's the kind of different perspective that you get by looking at it that way. Back to system 1 and system 2, the way we are dealing with this is by putting high throughput memory and low latency memory, microprocessors, and Dataflow on the other side. And that way, I guess we've lost the sound on this one. But you can imagine that this was, there we go. Very nice. So you have the assembly line idea of getting things done more efficiently. And then you have the artisan here who goes and does the whole thing. One program, he goes through the program step by step and does everything that it tells him to do. And there's some collaboration needed because obviously these guys individually don't know what they're building. And this guy here is not necessarily worried about how long it's going to take him to make his artistic component there. And so the collaboration of these two is the way we are putting these together. So now moving on to the programming interface. If you, let's say, have a convolution, which is a very simple standard computation, and you say you have this program and it goes through the loop and coefficients, and you have a two-dimensional array, and you want to compute this stencil here that looks like this with coefficients 1, 2, 3, 0, 1, 2, 3, 4, and you want to express that as a data flow architecture. The way we are writing this is simply the same way as it would look in a regular program, except that your index into data turns into delay FIFOs on the hardware side. So you're now having, instead of a register file, you're simply storing the numbers locally inside of these little memories. And if you write it this way, which is very similar to this here, except that the index now becomes memory. And that local memory allows you to stream the data from one side through the stencil back out without having any events, without having any memory access, other than, of course, the input stream and the output stream. and also allows you to cascade these down. How much memory do you need locally? Well, locally you need as much memory as the distance between the coefficients. And so now the job goes back to the scientist to say, what is the stencil that you can build that minimizes the distance between the coefficients? And most people may not have thought about the problem that way, that they can optimize computation by looking at the distance between their coefficients in their operator. Yes?
Yeah, this looks very similar to the way you program a GPU.
Maybe.
Okay.
Yes. So there may be similarities to all kinds of things. It is thinking about where the data is and where it's going. And so you have the same thing on the GPU. You have to think about when the data is moving from one side of the PCI Express bus to the other and which memory it sits in. So that's kind of the level of similarity, and that kind of gets expressed in your description.
I would disagree with that statement, because what you're doing is you're allocating specific hardware resources, and the GPU is, I mean, as we sit here now, they have caches and so forth.
Yes.
I mean, difference being they just don't have coherency in the caches.
There are some things that are slightly similar, and there are some things that are very
But
different.
there's no specific allocate. You're allocating a resource for the coefficient that's going to stay there the entire time that your data is streaming through the stencil. The
Yes.
GPU is going to rely on a texture cache or
That
something.
part is different. Yes.
But no, I'm going to go, saying I program this algorithm, I'm going to explicitly allocate or assign part of shared memory to store values I'm going to use over and over again.
I don't.
Yeah, the other similarity is programming in terms of kernels.
Well, that's fine. I find the hardware description to be very different from writing a
This is-
kernel of a thread in software.
This is really computing in space. You're describing the structure, while programming the GPUs is describing threads of computing in time. So that's a difference. The similarity is that you have a heterogeneous system where there is the main system and then there is something else on the PCI Express bus, and you have to worry about computation here and over there. So there are some things that are similar and some things that are different. I think we should be able to agree on that kind of general statement here. The main point that I do want to make is as you stream this data through, you just have a function call here, and then you stream it through the stencil and you get it back out. You can now look at the real stencil. So now at the real stencil, again, thanks to our collaborators in the geophysics department here, we have some actual real stencil here, and so you have a lot more coefficients. Now the difference here is that the distance between this point and this point in the 3D array can be quite large. And you have to store the entire thing in the local memory. And so one way to optimize this, if you look at the CPU code, you have the inner loop, which is bound by the amount of local memory, the outer loop, where you have the time update, where it's, I guess, main memory bound, because you have to hold the entire array in main memory. And so on the CPU, the time is determined by the number of coefficients. So the less coefficients you have, the better, because every multiply takes time to actually do the computation. For us, on the other hand, that's not true. And there was this paper that we wrote that uses more coefficients, but the distance between the top and the bottom coefficient is smaller. And it turns out that this here can be, well, at the top about 3 times faster. So that's 3 times faster by using a different stencil. Of course, I couldn't develop this stencil, right? I have no idea how this stencil is being developed. I need to talk to a domain expert to figure out how to change the physics around so that I can have a stencil that looks like this. And then, of course, the impact of these on the time steps and on the discretization in space is all left to be figured out. But at the same time, I can say, if you could do that, hey, it runs a lot faster. And it turns out it's possible. So that's one example of an optimization that is enabled by this new technology. It turns out this actually runs in the same time or slower on the CPU. And it's not an optimization that you would typically do or want or look for in any system that computes in time. but when you compute in space, turns out it's very useful to have. And so that was a very insightful result a while ago. And so looking back at the applications, where do you use such things? Well, the application with the finite difference and it is used in imaging. So you have these boats and they go across the ocean. And then you can look down and image underground 3D images of the Earth to see the various layers by solving the acoustic wave equation. There is a wave going down from the boats, hitting the rock, cascading back up. And you have the largest moving object here that we can see from space, which are these cables 10 kilometers long, all full of sensors that help to do that imaging. And so in this environment, you have a tremendous amount of data hitting these boats at every second. I mean, basically, more than 1 gigabyte every 10 seconds. And so that's the one to compute on. And then you look at what did people accomplish with this in terms of actual performance. So here is an example published by an oil company of using these Dataflow computers and saying, well, this is using 8 cards, each card, maybe 50 watts, 70 watts, something like this, and measuring the actual performance. This is the problem size. So here is a small problem, a bigger problem, an even bigger problem, and a gigantic problem. And on the gigantic problem here, you see that the actual equivalence of these 8 cards goes to 1,900 CPU cores. You say, well, how is that possible? Well, it's such a large problem that didn't fit in the local caches anywhere. It didn't fit in the memory systems. And by building a computer that has enough memory, that has enough space to hold all of this locally close to the compute and computing on it at the same rate close by, you can actually achieve, at the corner cases, very extreme things. And so then finally you get something that looks like this, where the wave is propagating and you have that simulation. And you can look at that in real time on your screen rather than as a batch job overnight where you come back in the morning and you say, oh, how did my simulation work out? Oh, now I have to change my model. Salt may not be going this way. It may actually be much bigger. So that's kind of the environment here. There is another example. We now have a university program where scientists are studying how to put algorithms onto this architecture in a variety of domains. This one is astrochemistry, looking at images from the Hubble telescope here, and then looking at different chemical compounds in space and figuring out which ones might be out there, what the stars or whatever else is out there may be made of. And again, as the problem size increases, the Dataflow computing solution picks up. And it's not that it's faster than the competing technologies. It's really that it's less slower than the competing technologies as the problem size increases. And that can be a significant advantage as long as you have a big enough problem. So for small problems down here, it doesn't make any sense. As you increase the problem size, you see the uplift of this way of doing it. Here's another one, numerical example done for the Pitaevsky equation. There is another one here for microscopy, where you have very, very large images coming from the microscope up into the compute engine. And you want to differentiate and distinguish very fine bits in here. Simulations of the brain are very, very popular these days. So also very compute intensive. It looks like everybody wants to build a computer that works like the brain. And so this is at the University of Chicago. They've implemented this model which studies the different connections and links between the different cells. And they managed to simply simulate much larger systems than they could simulate before. So it's not so much about saving time all the time. Sometimes it's just about being able to compute a much larger problem and putting that into your engine. Here's another one, which is a bit more of a mystery to me, just from a scientific perspective. But that's a project running at UCL, looking at the different chemical structures. And there is a variety of other things. There is earthquake prediction, there is nanophotonics, there is graphics virtual environments. We have a real-time requirement to move data in and out of glasses, of screens, of things on the walls, on tables. There is, of course, the bioinformatics field, which requires a lot of data. So looking at all of this, one question may be, okay, so what kind of algorithms really fit well to this type of technology? And as I've said, of course, the problem size is a very big component. So having a big enough problem is very key. But then algorithm-wise, convolution, finite difference is kind of the trivial one to explain and the easiest one to catch. At the same time, conjugate gradient optimizations, things where you have large amounts of data that need to be computed on over and over again, where you have a static understanding of how the data is going to move through your system. You just have to look at the entire set of data all the time to search through it. Finite elements, sparse matrix solvers, are a little bit more tricky. Now here, that is one of the key applications that is really hard to parallelize. And so people achieve parallelizations of maybe 10, 12, 20, and are really excited about it. Most finite element solvers run on workstations because a large parallel system wouldn't actually make a difference. And so over here, you can think of the challenge as building the optimal memory controller for each one of these sparse matrices and representing the data in its optimal way. And again, here, this is a publication that came out here at Stanford at Hot Chips a while ago, where Schlumberger showed how they could actually improve on their performance of these types of algorithms. There is some database work, again, something completely different, far out on the data side, encoding, how to match up large amounts of data. Some great work being done here at Stanford. The Computer Systems Lab. And then finally, or maybe actually primarily, very interesting for finance and risk runs. And so I'll just pass on the stage here to Stephen to tell us a lot more about what it means to compute a lot more when you're faced with risk and operational situations out there in the field. So let me just do that. May not be as easy as I thought. Yeah.
To the slides where you compare a local table and some logic operation. Yes, yeah, here. I think you're comparing tables and operations, right? But I think table is not the only way to do one operation in one step. I think we can build some kind of specific circuits, like for example, in an extreme case, if we only take one operation like AND logic operation, so we have 2 inputs and 1 output. If we are using a table, we need 4 memories, right? But in operation circuits, we only need 2 or 4 transistors.
Yes.
So this is equivalent, and like memory is equivalent to circuits. So for more complicated programs, we can also do some kind of things.
Yes.
So has anyone done this kind of work that transfer a function into a circuit instead of a table?
When you say circuit, do you mean a logic circuit?
Anything.
So in fact, you can transfer any table into a logic circuit by just looking at the table as a truth table and doing logic minimization on the table. That's typically equivalent. Okay. You can think of the table as one table, or you can think of it as lots of little tables. And then the question is, how many tables do you need? Right? So I'm simplifying here. Right? So there is a way to think of it as multiple tables. Then there is a way to combine tables in a different way. Right? And then there is a way to do arithmetic in a different way. Right? So there's a wide range of options that you have here, and I've just shown a little one. In real applications, we have looked at geophysical applications where you cannot store the entire data in DRAM. And so you have to store it back out to disk. And so instead of storing the entire data back out to disk, we could also recompute it over and over again as we do our iterations. Because computation for us takes space and not always time, we can do some recomputation in available space without slowing down the computation. And so trading off, in solving PDEs, trading off the storage of data as it is going out with recomputing it every time step, which may look as inefficient, but ends up moving less data around. So you can think of having a computation and you compute forwards and backwards in the computation. And you can do that over and over again to save having to remember what that number was. So instead of remembering, you can always recompute. And that's what this is trying to explain, to trade off as well, except that this is easier to show. You can trade off remembering what the number is with the way to get there, right? You can remember a telephone number, or you can remember the person who knows that telephone number. You just ask them, right? And so that's the...
I'm sorry, I'm not very familiar with your specific techniques, but okay, I have got my answer for my last question. You can minimize the table.
Yes.
Yeah,
of course.
And another question is that I think this is kind of, like use a trade-off. You're trying to use more memory to get to save time, or to use time to save memory.
Yes.
So have you got any kind of equivalence, like 1 second equals to 10 gig of memory, something like that, or in more general circuitry? Do we have
I think that kind of equivalence between time and space in computing and space in memory is very application dependent. And so it depends really on what you're doing, and you would have to derive that yourself as you look at a particular application. What we do is we would look at Excel spreadsheets and create a little model of that computation and say this much data in, this much data out. And typically by putting together 20, 30, 40 numbers on a spreadsheet, you can model the underlying activity, and you can trade off the two sides very nicely. So it's all about modeling the computation as a flow of data across a system. And if you know your bandwidths across the buses and you know the capacity of your chips, then that is not very difficult.
Then last question. I think one program can have internal states, right? For example, I input a 1 inside the program. It may give out 0 or may give out 1,
yes,
depending on which state it is in. So, but a table is not. I think a table don't have internal states, right?
Well, the tables, this table is a read-only table for computing. But it turns out inside of our chips, you have SRAMs. And so you can read and write them at the same time. You could think of this table as something that can be written and read at the same time.
Okay, yeah.
And so if you just have lots of these, and you can read and write all of them at the same time, you can think of it as state.
The table is writing to itself, or
it could do that.
Oh.
It could also store it. You can tell it that it should be just storing it and remembering. It doesn't matter. So that's just a feature of SRAM. You can make it remember, or you can make it change itself.
For example, I'm treating a program like a black box. I don't know. Okay, I am not giving any dynamic instructions to it. I give in one data, and it pops out another.
Yes.
And this, I give the same data. It may pop out different data because of its
internal state.
Yeah.
Yes.
Then can a table do this too?
This table can store state. Yes.
Okay.
Any more questions?
I think if you store the table state, you still need some kind of operation units inside. I mean, processors inside too. I mean, the table is not purely a memory. It's a combination.
It's a pure memory.
Okay.
It's a pure memory, and there is also, you can create any logic circuit out of memory, because a logic circuit is a truth table, is a memory. And so they're equivalent. And so you can create any functionality out of both memories and logic. It's the same.
Okay.
I have a question about the physical map back to power. So CV squared F, okay, makes sense if we've got a chip or something. But if we're looking at something like, for example, gates that propagate, that are a clock tree or something like that, then the problem space becomes a little more complex because we have optical alternatives. Have you explored those, and is that part of your strategy?
We are not making any chips ourselves, and so we are reliant on the research of chip makers to make use of these technologies, and I am certain there is some great things coming up on that front, and so we'll certainly make use of this to trade off again one kind of resource with another kind of resource on the lowest level in this case. So yes, I think that could be very useful. Okay.
What I'd like to do now is turn the problem slightly differently. And just look at some of the more practical sides of what we've been doing with the technology and how we've taken the more computational side in geophysics and pushed it into the finance side of the world in a more generic way. And just start really with the notion of risk. It was quite interesting when I actually looked it up. Someone asked me what risk actually, what was the origin of the word, and it's quite confusing. There's the Greeks claim it, the Romans claim it, the Italians claim it, the Spanish claim it, the French claim it. But today we basically talk about risk as being any deviation from an optimum solution or process, usually described in terms of expected loss. The expected loss didn't just pop out of the woodwork either, and this is a kind of just a bit of a tongue-in-cheek skip through history. Trying to give you some feel for how risk came about. Kind of pre-1494, Pacioli's coin-tossing puzzle solution, there seems to have been a general view that risk was kind of fate. Just kind of, it happened. It was kind of the will of the gods. It just was there. And then in 1494, Pacioli was sitting there tossing the coins and figured out there might be a solution to it. And then there was a whole bunch of probability theory solutions and Bernoulli's law of large numbers. And interestingly, even some of the Bernoulli arithmetic is still used now in a slightly bizarre way by some of the exchanges. 1738, de Moivre develops a normal distribution. And I stand to be corrected on any of these dates. I tried to check them to at least two sources, but I could be wrong. 1763, Bayes develops his idea of prior beliefs. And in 1800s, finally, the theory of expected loss was developed. And kind of bringing that up to date, we got from measurement to precision in only 50 years, which is quite interesting. 1952, Markowitz developed the idea of diversification. Don't put all your eggs in one basket, especially if it's mortgages. And then in 1964, Sharp and Lintner developed the capital asset pricing model, a way of looking at the market and comparing things to sort of the average market return in a very simple way. And in 76, Ross developed the no arbitrage theory, and we were kind of off to the races, that it was then the idea you could replicate any risky security by a combination of a risky and a riskless security, and it was always possible to price things on a no arbitrage basis. 1992, Farmer and French pushed that into the multi-factor area, and they started thinking about risk across multiple factors. And then in 1994, and I don't claim this as a kind of a JP Morgan thing, but it is a recorded fact. 1994, Dennis Weatherston, the then chairman of JP Morgan, was sitting at a board meeting one day and said, "I'd really like to know how much on a daily basis we could lose just on an average kind of day, let's say with 95% certainty." And he said, "Oh, well, 5 days forward, 10 days forward, 15 days forward, just tell me how much we're likely to lose with a 95, 97, 99% expectation." And so value at risk was what it was known was born. And very quickly, because of a bunch of things, but not least of which JP Morgan had a lot of representation on the Bank for International Settlements Basel Committee, the VAR idea, value at risk, became adopted as standard in 1998. And so everyone's kind of been focusing on that since. But what's actually more interesting in some respects is to think about loss versus risk. And we can think about really categorizing risks and losses based on the degree of severity and the frequency of occurrence. And there's definitely a bit of confusion going on about probability and frequency of occurrence. There's this kind of insistence and innate belief that I can assign a probability. I can say I'm 62.7% certain that the shares in Apple will go up by 1 cent or more tomorrow. And one of the things I quite like, we've been driving around in the Palo Alto area over the last few days, and I particularly like your fines. There's the $1,000 fine, which I can kind of understand. That seems like a reasonable, rational number. Then there's the $281 fine and the $336 fine. Now, I'm not quite sure that precision is kind of intended or accidental, but there seems to be this kind of idea that obviously that fine in some way relates to some probability or frequency of occurrence. They must have come up with that number from somewhere. Hopefully they didn't just go, 281 seems like a good number today, it's a Wednesday. So trying to categorize risks and losses and think about the one against the other. And so looking at the log of the frequency versus the log of the severity, categorizing those risks into kind of immaterial losses where expected losses and risks are negligible. Things happen on a daily basis, you kind of lose stuff, and it's kind of part of doing business. And then the top corner, nominal operational risks, where expected losses are more important than the risks. So the actual loss or the shrinkage is actually more important than the risk that you're taking. Ordinary operational risks, where we both expected risk and the expected losses are significant. And then down here on the right-hand corner, which are the much more interesting ones, where the risks are much more important than the expected losses. And there we're thinking particularly in a wider context, when you get situations like UBS suffered, where a trader took many billions of dollars worth of bets, and it wasn't the size of the loss that was important, it was the impact on that institution's reputation. And the consequent loss of confidence in the institution, and the fact that many, many, many billions of dollars drained out of the institution because there was a belief that actually that institution didn't know what its risk was, didn't know whether or not people were trustworthy, didn't know whether or not they could measure the risk correctly, and therefore couldn't control it. And if you can't measure it, you can't control it. So really trying to link losses together. And kind of pushing the problem slightly into a different dimension, uncertainty and risk. And I am eternally grateful to the now well-quoted Donald Rumsfeld as the unknown unknowns. Uncertainty, I think, is probably the best definition going. But I particularly like the side comment that he also made, which is much less reported, is that what really hurts you is the known knowns. These are the things that you know, but you don't want to admit you know. And they're the things that are going to cost you the most money. And so really, uncertainty, no probabilities. We've got no idea, we've got no probability distribution, probability of the Third World War. Well, I don't know. Could be one, might not be one, might be happening now, we don't know. But what we're trying to do is to model, in some sense, produce a model of dynamic behavior to contain those uncertainties, if you like, and come to something that's actually measurable. So now we can hopefully come up with known unknowns. We actually put some boundaries around this. We can measure probabilities, however subjective and however sort of ephemeral they are, we can actually come up with a probability. And a good example of that is in the credit derivatives market, where there are default curves for pretty much all the major names. And they get quoted and they get written every night, and people look at them and they value securities. And they're all absolutely certain that there is a 96.71% probability that the government of Italy will default in 30 years' time. Not quite sure where that comes from, but allegedly that's there, and everyone marks it every night. And interestingly, they all expect a priori across the industry that if that were to happen, there would be a 40% recovery. In other words, you'd lose 60%, but you'd definitely get 40% back, and all the banks use it. So probability, interesting. But are frequency, likelihood, and chance the same as probability? Because we do seem to mix them up when we try to measure risk. So what we're really interested with the Dataflow technology, if you like, trying to bind the thing back, is that down here, many institutions look at point estimates, and VAR is a really good example of a point estimate. We are 95% certain that we won't lose more than $120 million in the next 7 working days. Point estimate. And interestingly, if you've come up with a VAR estimate, once the loss goes beyond that, the simple VAR methodology has nothing to tell you about how big that loss might be, what it might look like in the tail. Even if you try a different probability distribution, it doesn't really tell you anything. It says, okay, now you've lost a lot more money. That's interesting. And if you read, there's a very interesting comment, you can Google it and find out on Bloomberg. One of the Bloomberg reporters did a kind of a very surgical dissection of the recent loss by JP Morgan, and I can kind of talk about it now I'm not there, and look back with a sort of certain amount of detachment. And he went through day by day by day and how they actually managed to lose $8 billion from when initially they thought they were only going to lose $1 billion. And very interestingly, right in the middle of the process, they changed their VAR methodology. And the VAR methodology, between day 1 and day 2, halved the amount of VAR. And so suddenly they're off to the races. They could double their risk. And so really what they were doing was, if you like, they were assuming that the numbers down here were good. Yeah? Actually, they were saying they were very confident about them. And they were assuming really that the models were deterministic. They were avoiding the complexity and avoiding the uncertainty. And what we're trying to push the technology here towards giving people is the ability to look at non-deterministic models via scenario planning. So expanding the universe and thinking about the measurement problem much more deeply. So why do we use scenario analysis? Why is it important? Well, to give us a dynamic response to risk. So in particular, linking actions and choices to outcomes of uncertain events. In other words, we should be better prepared by evaluating sequential and concurrent events. Not just saying, right, okay, let's bump interest rates and see what that means. What really hurts you are the combinations of events. And a good example of that is when multiple firms go bankrupt. So if you have one default, let's say GM defaulted, GM defaulting didn't hurt that many people. What hurt was the clustering of defaults, consequent increases in cumulative likelihood of events occurring. So one firm went down, another firm went down, another firm went down. And typically, not many risk systems can evaluate that. They typically look at one scenario, draw the lines and say, that's the number we're exposed to. They go to the regulators and they say, actually, we are 95% certain we won't lose more than $120 million in the next 7 days. So, dynamic response to risk. Value of information. Scenarios are very useful for getting a perspective on the value of information in decision making and reducing the error rate and avoiding short-termism. Typically, a lot of risk in the financial system is focused on making a short-term gain. It's not an accident that financial institutions revalue their trading books every day. And in fact, the more enlightened ones are running and revaluing them and calculating the risk in pretty much in real time. Now, does that actually improve the process? No, but what it does do is that feedback route does begin to reduce uncertainty if the measure is correct. If you're looking at the wrong measure, then you're still screwed. But if you're actually thinking more widely about the measure and you're computing more frequently, it's a sort of a robust optimal control argument. You've got a feedback system in there and you're beginning to reduce the uncertainty. And then finally, risk management. If you've got better response, you've got better information and you're using perspective, risk management should enable you to decide proactively and act on those events that should be guarded against. And so avoid double counting or missing of risks. And that's really the driver for why we've been doing what we've been doing. So how do we go about the scenario process? Well, clearly we have to identify the factors, what things are going to cause a problem, why, how, and establish behavioral equations. Then we determine the number of scenarios. I mean, how many scenarios do we need? Is the answer 1, 1,000, 10,000, 100,000? People think of these things in terms of the normal distribution. So clearly we do 10,000 and we should get convergence. Well, actually, if you've got 1,000 different factors feeding in, 10,000 scenarios isn't going to be enough. Is 1 million enough? Well, then you begin to look at the asymptotic behavior. Do you get actually stability or do you just get kind of noise at the end of the curve? And so determining the number of scenarios is actually quite a tricky thing because not only do you need convergence, but you also need to think of computational cost and time constraints. So it's no good running a big scenario with lots and lots of paths and lots of simulations if it takes you 6 weeks to do it when you need the numbers right now. So speed and the ability to contain and process large quantities of data very quickly are key in this kind of area. Then obviously we have to be able to compute the cash flows and event payoffs. Just doing that is actually quite an interesting exercise. And looking at the changes in value associated with assigning the probabilities can actually be an interesting exercise. In a lot of cases, the accuracy of the information feeding the cash flows is far from good. Typically, take bonds, for example, where a lot of the banks lost money trading bonds during the meltdown. A lot of them pull the information off Bloomberg. Well, actually, the accuracy of the Bloomberg data is only as good as the people feeding it. And if the people feeding it are under pressure and they're trying to trade like crazy, then guess what? They're not going to be updating the Bloomberg information, and that's feeding everyone else. So you do have to be very careful about then assigning those probabilities and looking very carefully at whether or not they're objective or subjective probabilities. And when you're assigning probabilities to a scenario, are you saying that's your central scenario? Are you planning your institution around that? What are your views on the actual wings of the situation? So let's apply that more generally then and look at some cases. How will scenario analysis help me in my portfolio? Should I invest in the S&P? If so, how much and when? And if I invest, how should I protect my investment? Well, this shows the S&P going back quite a way. And you can see there's a really nice pattern there. And you can kind of, in historical terms, clearly you should invest at the bottom and sell at the top. And it should be a very simple thing, walk away and we're all rich. Why is that not the case? Well, it turns out that it's actually not that easy to achieve that for a whole variety of reasons. How do you now measure these things? Should you look at the price to earnings, price to book, price to cash flow, price to sales, price to earnings to growth, or the dividend yield? Each one of those things will give you a different view of how your portfolio should look, and more importantly, how you should change your portfolio at any instant in time. And so it isn't as simple. If it was that simple, I wouldn't be here. I'd be sitting in the Bahamas with a large stack of money. So it's not as simple as it looks. So we need coverage. Information, again, is interesting. Global events, as Oskar mentioned earlier, kind of looking at tsunamis and hurricanes. I mean, one of the interesting things with the Japanese problem that they had was they looked at tsunamis and they looked at hurricanes, but they didn't apply it to what would happen if you had a nuclear power station right on the coast that was on a fault that was going to get hit by a tsunami. And so actually looking at consequential series of events, the ability to model in higher dimensions and think more rationally. But this applies to both ends of the time spectrum. On the one hand, you have a kind of a macroeconomic overview, but on the other hand, you have rules-based algorithmic trading that is working almost in real time across a lot of the markets now. Other problems. This one I quite like as a problem. I'm most certainly not a geophysicist, and Bob will tell you that absolutely definitively. There's no problem there. But some of the information, I sat and watched 2 Stanford videos the other evening, which I found very, very interesting. The Deepwater Horizon problem. There was no mechanism for control of the riser or the blow-up preventer at the surface. So there's 5,000 feet of pipe from this floating vessel down to the floor, and then 13,000 feet of pipe to the actual hydrocarbons. So now, when things fail, you've got 18,000 feet of combustible fluids in a pipe that wide, coming at you at probably quite a good rate of knots. So when it hits there, when it hits your vessel, it's going to explode, and there's going to be a lot of mess and a lot of leak. And again, loss of power, that causes loss of power, loss of dynamic positioning of the vessel, and you've got a disaster. Disconnecting from the riser was too slow, and the blow-up preventer failed. And then part of that blow-up preventer failed to cut the riser, and so, well, failed to seal the pipe, and now you've got a leak. Now, interestingly, we were talking to a certain oil company this morning about this kind of idea, and looking at the consequential risks. Looking at this event, and then linking it to this event, and linking it to this event. And their comment was, well, yeah, that would be interesting to do, but there's an awful lot of work and an awful lot of computation, and we've never really been able to do that before. So we're trying to broaden the thoughts on how our technology might be used. Here's another one closer to home, valuing a startup. So venture capitalists, and we've talked to quite a few venture capitalists this week, and it's been quite entertaining as an exercise. They value startups based on exit value using projected earnings on a multiple in the future, and then they discount the exit value of the target rate of return. Very simple and straightforward. So let's look at an early stage firm currently losing money, which is typical with early stage firms, but expected to make profits of, say, 10 million in 5 years' time. Nice round numbers. At which point the earnings multiple will probably be in line for the industry. Let's say it's a tech company, around about 40x. So VCs often use a very high target discount rate, say 35%, which would value the firm roughly at about 89.2 million today. So we've got two possibilities. The company goes public at 400 million, everyone goes home and is happy, or the company fails and is worth nothing. You'd be surprised at the number of situations that they don't look at in between there. They say, oh, well, let's just flex the discount factor from the discount rate from 35 to 50 and down to 20. There's a very interesting study that was done jointly by the Bank of England and the SEC recently about the impact of short-termism on discounting. And they looked across a whole range of markets and basically estimated a short-term discount, a short-termism impact in discounting. And it was actually surprisingly high. And the estimate was that across several markets, there was an over rejection of projects of about 25% due to excessive short-termism in the discounting. And basically what we're saying is that projects are getting thrown out the window because we're looking at them incorrectly. Now, is that the fact that the short-termism is a reflection of the risk, or is it simply a reflection of the fact that they're not doing enough scenarios to consider the breadth of the terminal values? Widening the debate from banking to insurance. You've certainly had a few hurricanes recently, and if you look at a banking taxonomy of risk here, we can think in terms of causes, events, and consequences. From the insurance point of view, we think of perils, exposures, occurrences or claims, and losses. And the interesting thing there is that we must be those data, to get a handle on them, must be capable of measurement and determination, as well as immune to manipulation. Otherwise, we have a moral hazard problem. I've got that just twice, sorry. So what are the commonalities in these problems? Well, high dimensionality, many causative factors, factor interdependence. Clearly there's a lot of feedback here in factors, one between the other. Factor ordering is critical. We can't simply run arbitrary combinations of factors, and that's what many institutions do. They sit down and they say, well, here's today's environment, we'll simply bump it by 50% up and 50% down. We'll do this and we'll do this, and it's very arbitrary. And effectively what they're doing is they're not spanning the event space. They're not doing it consistently. They're simply doing the combinatorics. And the critical thing here is to think about the permutations here, because ordering and combinations is actually critical when you're looking at risk. Whether or not a blowout preventer fails at this particular point, whether an explosion happens here, whether interest rates change here, which causes exchange rates to change there, the risk view is actually quite different, and you can't simply run arbitrary combinations of factors. So a permutative approach is required to span the event space. And then obviously we must need to run a lot more number of scenarios to achieve stable and robust results. And typically in the risk environment, there is almost always a very short time available to run those computations. Trading risk, just applying these, JP Morgan, 125 times faster, running the same kind of idea. But this is interesting now, is exchange risk. I'll just skip forward and I'll come back to this slide. So we started taking our technology into the low latency area for high frequency trading. Exactly the same data flow technology as we use everywhere else, the compiler, all the tools the same, and applying this for high frequency trading, where the turnaround time is in microseconds between the trades and the exchange. And we signed up a bunch of hedge funds and they started doing it. And right down in the low level of our compiler, we write a message. And so these messages started turning up at the exchange. Maxeler, Maxeler, Maxeler. The next thing we know, we get a phone call from the exchange. Excuse me, you're Maxeler. Why are we getting all these messages from you with Maxeler in? What's going on? Why are they faster than everyone else? So the next thing we know, we're talking to the exchange. And we've now applied exactly the same technology to redesign and rework their top of book, in other words, actually managing the flow of prices and quantities and the order matching process. The interesting thing about that is the execution and rejection rate. What feeds through from that then is, as you make the model faster, is there some kind of asymptotic behavior? And actually, how do you measure the risk at the limit? If these things are now being traded so frequently and so quickly, how do you measure the risk? How do you capture that risk? So, commonality of risk. Well, we've spoken a little bit about geophysics, financial modeling, etc. But what's interesting is the data flow-based simulation scales across problems. And I've just taken two examples here, which do illustrate the point. We can do black scholes. I mean, okay, black scholes, people say black scholes isn't used. Well, turns out the exchanges use black scholes. If you take the CME, they've got about 45 million live trades, of which about 30 million are options, and most of those are black scholes. So in any one time period, they're revaluing those and looking at the risk in a very large number of cases, pretty much all the time. So we can take 1,000 black scholes and run them 10 million times. So that's basically 10 billion in 11.4 seconds. The ability to turn that round is actually changing the way that exchanges look at risk, and we're beginning to move into that area as a very interesting byproduct. And at the other side, so that's a simple model, at the other side, a LIBOR market model, which is basically a multi-factor, three-factor model based around a sort of Monte Carlo simulation idea, and where we can run here 100,000 Bermudan swaptions going out 10 years monthly exercise on 30,000 paths for option. We can run that in 15 seconds. So again, pretty consistent speed up, 30. The technology works very well across both domains. So when order matters, what we're really interested in is running scenarios in an attempt to reduce uncertainty. Most scenario analysis is ad hoc. We need to think about key variables. Most scenario analysis is designed to find the worst case, okay? Minimax or maximin. Problem with looking for the worst case is often it isn't that instructive. Where you're going to lose the money is in the combinations of odd factors that don't necessarily give you the worst possible case, but because they occur more frequently, cumulatively you suffer larger losses. So what's our solution? Well, and this is kind of more interesting. One of the things we've done in the last 6 months since I arrived at Maxeler from JP Morgan is we've built our own finance library from scratch. So we now have a complete library where we have Monte Carlo, generalized PDE solvers, multinomial trees. We can do generalized cash flow generation. We have interfaces in Java, C, MATLAB, and Excel. And we can look at risk in different ways, regulatory, trading risk. But most importantly, we've built an engine that will do permutative and combinatoric risk and span the space very efficiently. And we cover all the major asset classes. The interesting thing about that is that not only is it available at a paying basis, but it will shortly be available, a stripped down and slightly simplified version to experiment with, will be available to our university program members. And as you can see, you're on the list, and there is a fairly extensive list of universities out there that are going to be trying it, we hope. Thank you. No questions? I'll sit down. Thank you.
So,
oh, I didn't get away that easily. Yep.
Yeah.
Sure.
So I think that Dataflow. You can just tell me if I'm wrong in what I'm thinking here, but you get this throughput-oriented result where you're going to produce a lot of results, but per the first talk, maybe they trickle out somewhat slowly, and this, in my mind, stands a little bit in contrast to my view of high-frequency trading, which is, as you said, in high-frequency trading, they care so much about latency. And so you have this enormous throughput, but in my mind, that implies a little bit more latency. And so it doesn't fully seem to match.
Well, on the high-frequency trading, we're pushing through much smaller amounts of data. Yeah? So we can, if you think about it in terms of kind of parallelization, we can push through lots more data. The data's simpler, but we can push it through much more quickly.
I can add to that a little bit. So it's not the data flow technology that reduces the latency. It's the fact that you have a network card, right? And then you have a microprocessor here. There's some network. You need to go through the network card, do your figuring out what the message is, get it across, interrupt the processor, do some computation, and go back here.
Mm-hmm.
While what we're doing is, you're saying there's one chip, there's a cable coming through.
You have the network on the FPGA.
The message goes through, that's right. Everything is right in there on the cable. So you put the TCP/IP engine and the whole computation on there in a loop with some stages and pipe it back out. So you save yourself the
So you could do the same with any network-enabled FPGA?
You could, yes. It's just harder to program.
Sure.
Sort of a philosophical question, maybe more for you, but like recently, a lot of the people are talking about exascale, and the problem for the exascale is energy. They say, oh, if we did this exascale, it would, require the 5 nuclear power plants or whatever it takes to run the exascale computer. And so I guess, is it, you got into this a little bit, but if you minimize energy, do you minimize your compute time, or is the reverse true, or is the real problem just minimizing the cost of doing this, period? Like, I mean, dollar cost? And have you done some kind of look, you say this is 30 CPUs, but did you calculate the energy per op, so to speak, of this computation?
The energy per operation is the real reason not to use this technology, because it's a meaningless measure that can be used to justify using very, very high-speed operations without having the data there.
I mean,
Doesn't make sense.
I didn't mean energy per op on like a micro scale. I just system energy.
So what we are doing is we are measuring at the socket.
Right.
So
Exactly.
we put the measure at the socket, and we say there's a certain computation that takes 1 hour, right? Takes 1 hour, and it takes this amount of watts during that 1 hour.
Yes.
And we are faster and lower power, and because of that, lower energy. So how much? Well, the total, the multiplication of these is between 20 and 50. So if you're 3 times faster, you can be 7 times lower power. If you're 5 times faster, you're 4 times lower power. So it kind of multiplies out that way. So you can slice it any way you want, but you can take a 20-hour computation and do it in 1 hour, or you can take something that requires a megawatt and divide that by roughly 20, maybe with some inefficiencies there, maybe divide by 18.
I guess it's not. I'm done after this for the sake of your question, but I guess the conjecture is if you really minimize energy, would you also minimize the computation time, or are these?
There's a trade-off. It's a trade-off. It's like there is no free lunch. You have the whole thing, and you can have more of this, or you can have more of that, and you can trade one to the other, but you cannot have both, right? So you're trading off advantage on one side with advantage on the other side. To get back to your question about exascale, exascale is a very interesting case in that really it cannot be done. And just recently it was announced that the exascale deadline has been moved from 2020 to 2025, 28, even though the Department of Energy did have a proposal that one company wrote that showed clearly that they could have exascale computing by 2018. And so computational speed and power consumption is being touted as the most important thing. But at the end of the day, there's a lot of other considerations that are coming in place when exascale is being discussed and then when technologies are being evaluated. So I wouldn't necessarily say that cost or power or compute speed are the #1 issues in exascale. A lot of it lies with legacy codes and with structures that are in place to deal with these legacy codes and what these exascale machines need to be used for afterwards. So that's
I think there have been a lot of recent developments to push up the performance of some of the FPGAs. For example, the achromic stuff. And some of that is kind of profound under the hood.
Yes.
But in general, at least it's my experience, that these things tend to have wrappers so that they very much look like legacy stuff. Does that imply that, in fact, if you got access to the internals, you'd be able to derive better efficiency?
Yes. So we have done a rough study in that if we were to make our own chip, we could be roughly 5 to 10 times faster. But that would also come at a very large cost and would require a very large amount of volume. And HPC as a whole does not actually justify making a chip, because as a whole, the whole market of high-performance computing is not large enough to do that today. So that's kind of the chicken and egg problem with these things. So we are stuck with prototyping them, which still seems to be good enough on some. Does that answer the?
Yeah, that answers. If there's time, I'll ask one more, which is there seems to be a lot of good activity in the drug discovery scene that is very much akin to this. Is that on your problem list?
Yes, we do look at not just drug discovery, but also the application of drugs to particular patients. So drug discovery is one thing that is touted a lot, but even more interesting from a patient perspective is, given that you have a certain problem, which of all of these drugs that are out there would be optimal given your genetic sequence, given your particular history, and given all kind of samples that you can take from that patient. And so that is a computationally immense problem that is very core to the idea of personalized medicine, trying to say what is the optimal treatment, not for the class of patients that have certain characteristics, but for that one particular patient and that particular set of cells that he may have with their genetic mutations or whatever. So yes, we are looking at these things extensively.
I think you talked about what kind of problems these techniques are good for. What are the problems that they're not good for?
Oh, I guess my quick question would, my quick answer would be problems that are simple, that are not real problems, things that compute in 1 second, things that have no data or computation associated with them, and then generally things that run very nicely and easily on microprocessors without any need to do them any better. So these are kind of the
Yeah, I was just wondering if there's
categories.
a classification of that second one that you said, that abstraction, that you could, like a type of problem. But I guess.
I mean, you can think of it as a technology that is really excellent at doing things that you cannot do with any of the other technologies because it requires more effort. It is always optimal to spend less effort. So if you can spend less effort, it's better to use something else. If you cannot use something else, then here is an opportunity to do something that goes beyond a certain activity, given a power envelope, given a space envelope.
I mean, I know of one problem, which is simulating gates, and it's kind of, it's in this category of it's time, it takes a lot of time, it takes a lot of resources, but people seem to just throw their hands up when they want to do some parallelism on it. I mean, I'm just trying to think of an example in response to you. Am I, like...
Well, that's EDA, and there's more money in floss than there is in EDA.
I mean, maybe that's the issue. Not.
And actually, it's an order of magnitude. It's being nice to EDA there.
Just throwing it out. It could be the market or something. Yeah. It doesn't justify the research and development, does it?
We have certainly students in the university program who are looking at that.
Who want to do some gates with DFE?
Yeah, some chip verification. Yeah.
Yeah, that'd be cool.
Yeah.
That'd be very cool.
Yeah. So there are people looking at this. It's just not a very high energy activity right now for us, but
Okay, cool.